It's a pleasure to listen to David Hume this morning from Oxford, and he will talk about coarse negative curvature in action.
Yeah, well, thank you very much. Thank you for the invitation to speak here today, and I decided to try and stick as close to the theme of the conference as possible. So what I want to talk about today is hopefully an informative program of questions you could ask for a group which has some kind of coarse negative curvature, has some kind of hyperbolic-like properties, to learn more about the group, and I'll explain as I go along exactly what I mean by this. So let me start off by talking about the kind of actions that I'm interested in, or kind of actions I'm going to talk about. So the main question is what nice, in inverted commas, actions does a group you're interested in admit on hyperbolic metric spaces? And while there are many very acceptable versions of nice for convenience, what I'll stick with in this talk is that nice will mean non-elementary acylindrical. So I am going to define this, or at least I'm going to draw you a small picture of it. This means that we have G acting on X, which is a hyperbolic metric space, and the non-elementary condition will tell me that it's not quasi-isometric to a point or a line. Okay. Hyperbolic space is a little bit bigger than these things. And what's the acylindrical condition? Well, so I have to get this right. For every epsilon, there exists constants r and n, such that the number of elements of your group, or such that for all x and y at distance at least r, the number of your elements of your group for which you can draw the following picture: here's x, here's y, at distance at least r, such that G moves both x and y a distance at most epsilon is at most n. So as a control, it's sort of proper on pairs of points sufficiently far apart, uniformly proper on pairs of points sufficiently far apart. Okay, so I'll keep that up. Here's the definition, which is going to be one of the main things we're going to be interested in. So we say an element G in G is a generalized loxodromic if there exists one of these nice actions on a hyperbolic space. So this will be non-elementary acylindrical, X is hyperbolic, and G acts loxodromically. On X, and in keeping with the theme of Alessandro's talk yesterday, I'll give you a theorem definition. So theorem definition due to Ossian is that this is one of the arbitrarily many ways of defining acylindrically hyperbolic groups. G is acylindrically hyperbolic if and only if it admits a generalized loxodromic element, which I'm going to start abbreviating. Okay? So there we are. That's what I've decided for the purposes of the talk, I'm going to mean by nice. So then I should at least motivate this. Why such actions? Why do I claim this would be an informative thing to study? Let me give you, so just one motivation, which is a theorem of Damani, Girardel, and Osin. Chalk. Okay. So if you're given such an action, so if G acts on X, and this is going to be non-elementary acylindrical, and X is hyperbolic. I should just start writing nice, but I'm going to stick with that. Then let me give you a slightly strong version. Then there exists an M such that every G and G which acts loxodromically on X, for every G and G which acts loxodromically on X, the normal subgroup generated by G to the power n is free. Okay, and the in particular may seem very simple. In particular, G is not simple. It's either free or it has a free normal subgroup. In either case, it's not simple. Which is not a property you normally have to consider too often when you're dealing with groups with some hyperbolic-like properties, but it's surprisingly interesting. And it's been very, very useful in the theory. Explain this part to you. Well, perhaps the example that if you know one, this will be the one you know. So a theorem of Cantor and Lamy. Now you would phrase as they found that the Cremona group, so the Cremona group, or a Cremona group in the correct dimension, the Cremona group, which is birational transformations of complex projective plane, is not simple. Okay. Although they don't phrase it this way in their paper because their paper appears before these kinds of definitions of acylindrical hyperbolic. Pardon?
You mean right, it's acylindrically hyperbolic?
Yeah, okay, it's acylindrically hyperbolic.
That's what they don't say in the paper.
That's what they don't say. True. So they prove it has an action on a hyperbolic space, which is not acylindrical, but the bad behavior is located in certain places which you can blow up, and then it's still not acylindrical, but you can repeat the process of blowing up over and over and over and over and over and over and over, and in the end, you get something that's still hyperbolic and the action is acylindrical. Okay. So this group has three normal subgroups. So if you know one, that's the one you know, but there's another one, and let me state it before I tell you the extensive list of references. So if K is the compact form, also called the orthonormal form, of a real split Kac-Moody group, so the compact form of is not simple. Okay, and the names I should attach to this is that this was first studied, convincingly conjectured by two high-energy physicists, De Moor and Hillman, who proved it completely to their satisfaction and to the satisfaction of people in their area, which was published in a great journal, much higher impact factor than the rest of them. This was then proved to the satisfaction of mathematicians by Gatte, Horn, Curl, and Weiss. And both of these proofs show that it has a quotient which is a non-trivial compact real Lie group.
Is there some assumption non-spherical?
Yes, non-spherical. Yes, I mean actually a Kac-Moody group, not a Lie group. Yes, not Lie. Kac-Moody group is a Lie. You imagine as an infinite dimensional Lie group in some sense. Okay, so yes, not a Lie group. Thank you. I thought you were going to tell me I'd referenced the wrong people. I was getting worried. So both of these proofs go along the grounds that K has a quotient which is a compact simple Lie group, a non-trivial one. But in fact, there's an argument of Kapas and myself, which is to add the brackets. It's acylindrically hyperbolic. And in fact, our result also applies to the kernels of the maps that are produced here. Okay, so they produce a map to a compact simple Lie group, and in fact, the kernel is also acylindrically hyperbolic. Okay, so they were studying this in order to understand what was it? It was fermionic Kac-Moody billiards and supergravity. Please, no questions about that. Okay, but how do we do the acylindrically hyperbolic part? Well, actually, K acts not quite as described here. It has an action on a on delta, which is a Cat0 building. And the point is that there's somehow enough negative curvature in gamma, and the action of K is sufficiently nice that although this thing isn't hyperbolic, you can still pull out the same kind of conclusions and actually make an action on a hyperbolic space out of it. Okay. So this is what's motivating my talk for coarse negative curvature in action. I don't really want to just consider actions on hyperbolic spaces. I want to allow myself actions on spaces with sufficiently nice hyperbolic properties. Okay, so let me see. Next, okay, so the sort of question is, what is the relation between these actions as I've described them and, if you like, some coarse negative curvature? In G, or in nice spaces that the group in the group, or in nice spaces that the group act on. So the definition, how am I going to describe this kind of coarse negative curvature? Well, classically there are two ways of doing this. There are two elements of coarse negative curvature you use when you're studying hyperbolic groups. So one of the first things you want to do with hyperbolic groups is show that this notion is somehow quasi-symmetry invariant. And to do this, you use what's called the Morse property, which is a form of coarse negative curvature. A second thing you really use negative curvature for is when you try to do some boundary dynamics to show that non-elementary hyperbolic groups have free subgroups. And they're using something that's really a lot stronger than the Morse property. And so let me try and describe what's going on there and what the difference is. Okay, so let me, for reasons of simplicity, I'm going to have Y is going to be a closed subset of X, which is going to be proper geodesic. Okay, so here's my picture. I've got Y and X is everything. Okay. So we say Y is rho contracting And here rho will be a function from 0 infinity to itself. And I'll ask that rho of r over r tends to 0 as r tends to infinity. Such that the following happens. I take a ball, so B will be a ball around Z of radius k. What am I interested in? Okay. And so this rho contracting says if for all Z and k such that the distance from Z to Y equals R, which is strictly greater than K. Okay, so just that this ball is disjoint from Y. Its center is further away from the set than its radius. This is bigger. I will look at the closest point projection of every point in this ball to Y. So it won't necessarily be a point, it could be a set. I will look at the closest point projection. So this is the projection onto Y of the ball. So we have some contraction, that is the diameter of this projection is at most rho of r. So I start off with a ball that could have radius basically r, and when I project it has to, the diameter of the projection is at most rho of r. Okay. What is a version of this you're probably more used to? So what I'm going to call for the purpose of this talk strong contraction, which is exactly what you get in hyperbolic groups, is the case that rho of r is bounded. So any ball disjoint, so if you've got a geodesic in a hyperbolic space, so we have a geodesic, I'm a geodesic in a hyperbolic space, this will be strongly contracting with a constant just depending on the hyperbolicity constant. And this is the form of coarse negative curvature you use when you want to prove that the action on the boundary has north-south dynamics and your group has three subgroups. Okay. So let me just tell you. That's up more space. Okay. So this is a kind of spectrum of different types of coarse negative curvature you could have. So theorem which proved in at least in great generality in a paper with Gunnar Agentseva, Chris Cashin, Dominic Gruber, and myself. So I only have 3 co-authors to tell me if I've got it wrong. Is that a geodesic is Morse if and only if it is rho contracting for some rho, with this condition that I wrote, such that rho of r over r tends to 0. So as soon as you have any one of these contracting conditions, you're Morse. Okay. So I want to know what the relationship is between these actions on hyperbolic space and this negative curvature you can have in a group. And there are 2 big results in this direction. The first involves a lot of this actions on quasitrees work of Espina, Bromberg, and Fujiwara, but then has to be so you get one definition from Espina, Bromberg, Fujiwara, and then need some results of ozone just to make this absolutely concrete. So let me give you this is going to be a very specific case of it. So you have a finitely generated group, and G in G is of infinite order and undistorted. If the subgroup G in G is strongly contracting, then G is a generalized loxodromic. So if you have the really strongest version of negative curvature in a Cayley graph, then you're automatically a generalized loxodromic element. There's going to be an action of your group on a hyperbolic space, which is acylindrical, in which this element acts loxodromically. Okay, and the other theorem, the other extreme, theorem of Sisto, which says that if G is a generalized loxodromic, I was saying, then this subgroup is Morse. So this subgroup must have some negative curvature. Okay, so if you get the strongest form of negative curvature inside your group, you're automatically a generalized loxodromic. If you're a generalized loxodromic, then you do have, you can see some weak version of curvature. So the question is, can, or perhaps more appropriately, when can generalized loxodromics be understood via contraction? So this gets me on this board at the right time, because I want to write something I don't want to erase. So this is introductory workshop to sort of 5 months of getting lots of papers published and lots of things written, hopefully. So I wanted to ask more questions than I provided answers. This is sort of a key goal. So what I want to propose here is a program of study for your favorite group, which I think will give you a lot of information about it, and which is understood in a few cases, but wide open in a lot of others. So let's program. Program step 1, and it's an important one, is so fix G popular / interesting, or even both. So question 1, does G admit a generalized loxodromic? We've seen how useful that can be, not necessarily in finitely generated cases, but even for some groups that conjecturally a few years ago were simple. Okay. The second one, well, we know once we have a generalized loxodromic, we know some things about it. There's a power of it that normally generates a free group. So this is useful information to have. So the next question would be, can we classify the generalized loxodromics in G? Can you give me a way of telling whether a particular word I like in my group is a generalized loxodromic or not? And then 3 is, how hard do we have to work to understand them? Is there just one hyperbolic space, one action on a hyperbolic space, which sees all of the generalized loxodromics at once? So, does there exist action on X, I'll keep doing it, non-elementary acylindrical with X hyperbolic, such that every generalized loxodromic acts loxodromically on X. Okay, and that is quite a mouthful, so I'm going to paraphrase that as, is G universal? or universally acylindrically hyperbolic, or something along these sorts of lines. Understand it as. Okay, why would you care about such a universal action? Why would that give you more information? Well, it wasn't necessary when I spoke about it earlier, but now it becomes more interesting. There's a uniformity here. If all your generalized loxodromics can be seen in a single action, then there's a uniform n such that every one of these elements to the power n normally generates a free subgroup. So you get a kind of uniformity from understanding which elements can simultaneously act as loxodromics in one of these actions. It's a beneficial thing to know, not just to produce one action for each element, but to see which elements can simultaneously act loxodromically. Okay. 3 is plenty of questions. Right. So that's so far a list of theorems and a list of questions. Let's show some examples. Okay, example. So I don't know why I'm looking at this, it isn't on here. Examples. So to try and tackle some of these questions, let's say firstly that G is amenable, or satisfies a law, which means there's some word which, no matter which group elements you put in, you always get the identity. Okay, so for a solvable group of a certain rank, there's a law which is this certain collection of commutators. Certain iteration of commutators is always trivial. Or perhaps it's got uniformly bounded exponent. So every element to the power 5 is trivial. Okay, if this is the case, then the group has no elements whose orbit in the Cayley graph is Morse, or it's virtually cyclic. Should be careful. Okay, no, that's not important. Okay, so if it's amenable or satisfies a law, then it has. So it's amenable or satisfying a law has no generalized loxodromics.
Yeah, but it doesn't contain a free group, a non-abelian free group.
It fails my program at question 1.
Yeah.
Yeah, so it doesn't contain a free group. Right, so you can, yeah. But that way, and for the same reason, you can take some of these Tarski monsters. Tarski monsters. Even though they can have elements whose orbit is Morse, right? They still can't have any generalized loxodromics because they don't have non-abelian free groups. Okay, so that's good. Go into the case where I can't do anything. In the case where we hope everything is done, G is hyperbolic. So if the case G is hyperbolic, let's just then the set of generalized loxodromics is exactly the set of infinite order elements. Okay, every infinite order element is undistorted, and the action you want to consider is the action of G on any Cayley graph. And this action is universal. Okay, every infinite order element acts loxodromically on a Cayley graph. Okay, now definitely sticking with the theme of the conference, what about if G is cat 0? Well, in cat 0, by this I mean that the group acts geometrically on a cat 0 space. Nothing more than that. So recall that if your element is a generalized loxodromic, then its orbit in the group is Morse. So if it's got an orbit, then it will have an axis sort of parallel to this orbit. In a cat 0 space, in cat 0 spaces, a geodesic is Morse if and only if it is strongly contracting which is if and only if it is rank 1. Okay, so it's a geodesic that doesn't bound a half flat. So the set of generalized loxodromics is precisely those G such that the associated axis, well, it should be G's of infinite order, in which case they're undistorted, such that the axis associated to G is rank 1. Okay, but I've said nothing about producing an action on a hyperbolic space, or which elements you can do this for, or which elements you can do this together. So I think a very interesting question is when is a cat zero group universal? The only examples, and I'll tell you them a little later in the talk, of groups I can show that are non-universal are all infinitely presented. So even to find a finitely presented example would already be very interesting.
I'm confused about your definition of generalized loxodromic. I thought it had to act on a hyperbolic.
This is the magic of this theorem. It will produce for you a hyperbolic space on which your group acts, such that this element acts loxodromically. Okay, so this will produce one where actually technically you get a WPD action, and then you need a little bit of magic. Ocean shows that the definitions are equivalent to show you can actually get an acylindrical. So this is the tool that is producing from an action on a sufficiently negatively or space with some negative curvature. It produces for you an action actually on a quasi-tree.
So your then G as a generalized loxodromic conclusion is
precisely that they construct from this information a hyperbolic space on which this group acts in such a way that this element acts loxodromically. Yeah.
Right, got you. Yeah.
Yep. The magic. I could talk for the rest of the day on how you do this and not be entirely convincing.
I think I was confused actually when you wrote that up that there was no action mentioned in the.
No, this is the really amazing thing. There is that this is a purely geometric condition with strong algebraic conclusion. Right, this is really a sort of fascinating thing, and what's particularly interesting, there's a huge amount to say there, and if I start, then I definitely won't finish. So I decided not to start. But okay, I think this is particularly interesting. So let's see. I don't know. I certainly don't know of any example where of a cat zero group that's not universal or even suspected not to be universal. So all I'll say is that right-angle Latin groups are universal. They act universally on the contact graph. Is he in? Is he in? Where is he? No? Okay, never mind. Okay, so Mark Hagan has a contact graph, and the action of the right-angle Latin group on this contact graph, which is a quasi-tree, this is universal. Rumours from MSRI, someone has done right-angle Coxeter groups. Okay, that's all I'm saying on that. So, try and keep that board. And I kind of want to keep that board. Oh. One. Never mind. No, I definitely want to keep that one. Oh, too weak. Okay. So continue with the examples. If G is the mapping class group of a sufficiently interesting surface, there's an action of the group on the associated curve complex, and this is universal. the set of generalized loxodromics is exactly the set of pseudo-Nosovs. Yeah, it's a set of pseudo-Nosovs. All the pseudo-Nosovs act loxodromically on the curve complex, and anything that isn't a pseudo-Nosov is either finite order or fixes a curve, in which case it commutes with a Dane twist. So in the group, it's not going to be Morse. Okay. Let's move on to some interesting more interesting examples of G is relatively hyperbolic. So the first thing I learnt about this, first time I learnt about this universality question was a theorem of Carolyn Abbott, which says that Dunwoodie's inaccessible group at least one of the constructions is not universal. Okay, so this is a relatively hyperbolic group, which is not universal. And the problem is somehow that you have a collection of generalized loxodromics which are fairly easy to understand, but like we had this uniformity for the power n such that generalized loxodromics all raised to the power n normally generate a free group, there's a similar one for the index of a generalized loxodromic in its elementary closure. And all the torsion in Dunwoodie's inaccessible group allows you to break this. So you can't get every generalized loxodromic to act loxodromically on the same hyperbolic space at the same time. Okay, this is a very interesting, short, accessible paper. Sorry. Sorry, I'm leaving in 20 minutes. So just relatively hyperbolic is not quite how I would think about it. Instead, let's think about it hyperbolic relative to a particular subgroup. And I'm going to be interested in the questions I can answer on G based on the questions I can answer on H. This is the standard way of dealing with relatively hyperbolic groups. Okay, so the problem here is that if you do this, you just end up with basically the same group. You end up with the same problems with H. Okay. So, what are the generalized loxodromics? This takes a little bit of work. So, generalized loxodromics. Well, you certainly have those infinite order elements of G that are not conjugate into H, same as you would for hyperbolic groups. So you have those infinite order G such that G not conjugate into H. And then you also have those elements that are conjugate to generalized loxodromics in H. Okay, plus those G conjugate to generalized loxodromics in H. That's everything. Okay, you're either generalized loxodromic because okay, so I'll explain it correctly. So to see the first class of generalized loxodromics, you consider the action of G on a coned-off graph. How do you get the coned-off graph? You take a Cayley graph of G, and for every coset of H, so here's your Cayley graph of G. When you see a coset of H, you add a vertex, and you join with an edge. You electrify H. You basically reduce every pair of points in there to distance 2. This gives you a hyperbolic space on which the group acts non-elementary acylindrically. And all of these elements act loxodromically on this space. But that's not going to deal with the universality question unless H doesn't have any generalized loxodromics. So if H has some generalized loxodromics, we need to do something else. So let me find a board I've stopped caring about. Yeah, okay, maybe. Right, so a theorem which is about to appear, I've been saying for the past 6 months, so for Abbott, myself, and Dennis Ozin, is that if G is hyperbolic relative to H, and H is universal. Now let's be a little bit more general. H, and there exists an action of H which is non-elementary acylindrical on Y, which is hyperbolic, and some set of HI act loxodromically on Y. So all I know is I'm given an action of H which acts with some elements acting loxodromically. And what I want to do is produce an action of G where these guys still act loxodromically, and so do all of the infinite order elements of G not conjugate. So what do I do? Well, I'm going to cone off, but very badly this time. So what do? I take the Cayley graph of G, and when I see a copy of H, I glue on a copy of Y, and I attach elements of H to an orbit in Y. Okay? So you fix some Y0, and then you map, you get from here to here by applying H, you map this to H Y0. So you glue them along by an orbit. So this will all be equivariant. A group will act on it. This will Lipschitz map onto the coned-off graph, just by crushing the sets Y. And so this will have the properties you want, right? So then there exists an action of G on a space X, which is not on. The trick is to prove that that the action is still acylindrical, and the space X you get is definitely hyperbolic, such that every G infinite order which is not conjugate into H or conjugate to some one of these HIs acts loxodromically. Okay, so the problem with relatively hyperbolic groups, the problem with Dunwoody's group is its inaccessibility. Nothing to do with being relatively hyperbolic. Okay, if you could understand, have a sort of accessible hyperbolic group, and you can understand the peripheral, you can answer all these questions for the group. Okay. So there are many interesting questions. For instance,
the HIs still act loxodromically.
Exactly. So I started off with an action where the HIs act loxodromically, and I finished up with an action where the HIs and all the elements of G that are not conjugate to H act loxodromically.
All right, so I'm confused by every G that's not conjugate into H or conjugate to an HI.
So if you've got an element G of the group G, and it isn't either it isn't conjugate into H, or it is conjugate into H, but it's one of these generalized loxodromics, I collected the HI that act loxodromically.
Okay.
So this is precisely the collection of elements I want to act loxodromically in my new space. So you can take it, what I talked myself out of writing was if the action of H is universal, then the action of G is universal. Okay? That's the simple way of avoiding questions that I should have written. But,
Can I just clarify one thing? Is what you've drawn there a picture of the hyperbolic space X that you
exactly.
It's not just a space where you manage to show that everything's acting loxodromically.
No, that is the right
That's
space.
some magic to.
No, that is the perfect. As long as you started off with a non-elementary acylindrical action on Y, if you take every coset of H, attach a coset of Y to it, and identify an orbit, this space will be hyperbolic, the action will be acylindrical, all these things will pass. So basically, here we took a stupid cone off, like there were no generalized loxodromics. Here we're actually taking an informative cone off, where we cone off to something we already know. Okay, I think this is sort of a generally useful strategy. So you can think of it, if you wanted to get these guys to act properly, you'd attach cusps. rather than a point. And this is just an extension of that idea using an action you already know you have. Right, so now I want to pass to somewhere where questions are much more open. So I've got 10 minutes to do this. This is going to be fun. So my example, whatever number it is now, is G small cancellation. I should say graphical small cancellation. So I have to give you some idea of what such things are. So the idea with a small cancellation group is you take gamma, which is a graph with edges which are oriented and labeled by a finite set S. And you just build a group from this in the only way you could hope to try and make sure that gamma is a subgraph of the Cayley graph. So define G of gamma to be the group with generating set S, or S disjoint union S inverse, and the relations are the words you can read by going around closed loops in gamma. So labels of closed loops in gamma. Okay, why the edges are oriented, so if you follow the orientation in a loop, you write the positive letter, you write S, and if you follow it in the opposite direction, you write S inverse. Okay, so this will give you a collection, this will give you some generators and some relations. So it's a group, but there's no reason from what I've told you to believe that it's not trivial. So the small cancellation condition what it does here, two things. It, or the one ensures that gamma isometrically embeds in the Cayley graph with the right generating set. So Cayley graph of G with respect to this generating set S. And the second thing it ensures, so the small cancellation, it's going to give you that something I'd like to think of. You think of a group as hyperbolic relative to a subgroup. This is a group is hyperbolic relative to some subgraph. Okay? Everything that's not coming from gamma is hyperbolic. So all the behavior that's outside of, that's not being completely controlled by the graph gamma is hyperbolic. Just to give one idea of this, I'll give you a much more concrete statement in a moment. If gamma is finite graph, then G of gamma is hyperbolic. And except in really stupid cases, non-elementary hyperbolic. So a large group. Okay? And I want to explain to you what is known here. And I have 8 minutes to do this. So I said that I want you to think of these graphical small cancellation groups as hyperbolic relative to some subgraphs. How am I going to justify this? I'm going to justify this on the grounds that we really understand very well how contracting a geodesic is in one of these Cayley graphs. And it entirely depends on your intersections with these gammas. So theorem with audience members number 1, 2, and 3. Myself is that so let G be a graphical. So say myself a little time. It's defined by this defining graph gamma. I've got a labeled graph gamma. It satisfies the small cancellation conditions, and I've defined this group over it. Okay. Oops. And let gamma be a geodesic in a Cayley graph with respect to this generating set that was the letters I used to label the graph. Okay. So gamma is rho contracting. So if I want to understand how contracting this is, what I do is I look at, every path in gamma labeled by a subword of gamma is rho contracting. This is true up to allowing myself to distort rho by multiplicative and additive error. So this is, consider functions rho up to the relation f is at most g if there exists a c such that c times f of c r plus c is at most where's the one? G. If is at most g, no. Just start making things. G is at most f if g is actually at most some constant times this thing. So I'm considering them up to this equivalence relation. So f is equivalent to g if g is at most f and f is at most g. Okay, so up to changing this function by some small amount. Rho contracting is completely understood by just looking at the bits of your geodesics that intersect relations gamma, and if those are contracting, then your whole geodesic is contracting. You just look at it on a piece by piece basis. Okay, what does this say? It says that once you're not just troubled by a single relation, you think you're in a hyperbolic space. You're strongly contracting. Right? You're as strongly contracting as you can be. So using this, you can completely understand all these levels of contraction. You can understand the Morse property. You can understand strongly contracting in these graphical small cancellation groups. So let me give you so a corollary of this is that so an element, an infinite order element G in G gamma is strongly contracting if and only if there exists an n such that no subpath of gamma is labeled by a conjugate of g to the n. So if you have some uniform bound on powers that appear in your graph as labels in your graph, then the element is strongly contracting. Okay. And from this you can do some quite bizarre things. So it means that there are non-hyperbolic groups in which every element is strongly contracting. So every element is a generalized loxodromic other than the hidden element. So there exist groups which, to say it more accurately, are not subgroups of hyperbolic groups such that every non-trivial element is a generalized loxodromic. including some that contain expanders.
Is that how you know they're not subgroups of
There are
uncountably many of them, wasn't
there are uncountably many QI types of them. Yeah, actually trying to, without doing something like this, trying to show that any particular one is not a subgroup of a hyperbolic group is annoying. But if they contain expanders, then we're okay. That's perhaps overkill, but yeah, it works. Okay, so I am very nearly out of time, so I just want to tell you that while in my so I want to deal with my program for these groups, and I've told you a few things about them. So how does the program look for these groups? Okay. Well, the starting point is a theorem of Gruber and Sisto, which says that graphical small cancellation groups they are isolated kind of hyperbolic. They have generalized loxodromic elements. Okay, and then one of the results from this, from Seva, Cash, and Gruber, and myself, is we can explain. So we can explain all generalized loxodromics arising from strongly contracting elements. And all I want to say to finish are two results to say that generalized loxodromics in these groups, there's no other relation between the contracting properties I mentioned and being a generalized loxodromic. So two results with Carolyn Abbott. One is that for every function rho such that, let's see what I have to say, which one I'm going to do first, such that rho of r is unbounded and this sublinear condition, oh no, should be this tends to infinity and this tends to 0 as r tends to infinity. There is a G in G which is rho contracting but not generalized loxodromic. So there exists G, and okay, so you can make a finitely generated group and find an element of it which has the contraction property you want but isn't a generalized loxodromic. Okay, this is why I need this unbounded condition so that it's not strong, this infinite condition so it's not strongly contracting. And 2 is the same assumption for every there is a generalized loxodromic which is not rho contracting. So whatever function in between you try and give me, I can find you an element of a group that is that contracting but not a generalized loxodromic, or that is a generalized loxodromic but is not that contracting. Okay, so the theorems I mentioned of Best-Wiener, Bromberg, Fujiwara, and Ozin, and then of Sisto, they're the only two things you can say to relate to two problems. So deciding when an element in a small cancellation group is a generalized loxodromic seems to be a very interesting phenomenon. I think by understanding this, you'll know a lot more about generalized loxodromics and this acylindrical hyperbolicity. Okay, thank you very much.
Any question or comment?
completely understand the theorem that was on that board and then you erased it? More.
I've completely forgotten it now.
You said that it was about characterizing something in terms of subpaths of the graph gamma.
Right, so
You said you wanted subpaths of the graph gamma to be labeled by subwords to be strongly contracting.
right, so the point, so if you have,
Are you saying that, are you talking about finite or to be contracting? Are you saying that finite paths should be contracting, or?
well,
does it mean
for most
paths should be
applications and
labeled
most
by
things you will
subwords?
do, all the components of your graph grammar will be finite. This is
The
the,
paths, but you can have an infinite path, right? I'm trying to understand whether you want to only.
Oh, whether you're
finite
going to allow
paths
loops
whether
or
you
not.
want to- whether you want to-
I would say that's a finite. I consider that as a finite path. No, you want to understand finite paths, because if it carries on in a loop, then it's not a geodesic in the group. I'm interested in the geodesic in the group. Because these subgraphs embed isometrically, it must also be a definite path of a certain length in a graph. So there are,
And somehow projecting onto the end of a finite path isn't a problem because you just project a point in the diameter smaller.
yeah, this is, yeah, there's stuff you have to do, but the point, I underplayed it by sort of strongly delivering the intuition, and the hard work is in showing that our intuition is correct, that you have these graphs, and once you're outside these graphs, everything is hyperbolic. Behaves very hyperbolic. You have to really work to do this.
Any more questions? Comments? No? If not, let's thank David again.